So let's get started. So hello everyone, thank you for being here. My name is Tiejun Chen. I'm from VMware. Our team mostly focuses on machine learning AI, but actually beyond machine learning AI, I get involved a lot of things, from cloud native, edge computing, virtualization, and WebAssembly. So I'm always trying to explore if I can put what I'm doing in all these areas together to that RISC-V as well, to explore something out with RISC-V. I hope this can accelerate the adoption of RISC-V. So today I'm going to talk about one of these efforts around RISC-V. Back here, it's that Empower Machine Learning Framework on RISC-V by Backend Graph Compiler. It's something on machine learning for RISC-V. I hope this is your interest. Sorry. So let's go through today's agenda. First of all, I will give you talk some of the challenges for RISC-V on machine learning, and then I will walk you through our solution to address these challenges. It's about how to empower machine learning upstream frameworks. I also will show some demo to help you understand what I'm trying to do with this. In the end, just let's see what's likely next. So challenges. Talking about machine learning AI, the machine learning AI are the two of the fastest growing fields in the tech industry. Especially this year, I guess people pay more attention to machine learning because of that ChatGPT and the large language model. So I'm not sure how much you are familiar with machine learning. Just let's think of that general machine learning AI platform. Usually, we are being customized to use some special hardware accelerator, like GPU, FPGA, TPU, and others to do machine learning. Sometimes we can leverage CPU or some CPU feature like the AVX or AMX in x86 to do machine learning similarly, but with the wider performance. Besides this hardware, we also need software, device driver, toolkit like CUDA. But more importantly, we need the front end, those machine learning frameworks, such as TensorFlow, PyTorch, and so on. But what about this for that RISC-V? Actually, I think the typical role of RISC-V is to deploy the model on RISC-V-based system to do machine learning inference. Potentially, I think there are two cases for that RISC-V. Actually, I talked about this last year. So one is to deploy RISC-V-based hardware accelerator. The other is to deploy those popular hardware accelerators on RISC-V-based host. So anyway, these two cases are different, but there are some challenges in common. One of the things I'd like to mention again today is at that time, it was hard to have this machine learning framework supported on RISC-V. So what about now? After 1 year, what changed and what happened? Now you can see a few machine learning frameworks become available for RISC-V, like TensorFlow Lite and PyTorch. They can work, but I would say they just work with some basic support. At the same time, you can see many new RISC-V have been introduced with any kind of advanced machine learning AI extension. And most of the vendors just provide sort of that tool set, including that converter tool and that runtime typically. The converter tool can help you convert that model pre-trained on the machine learning framework on other architecture to such intermediate repetition to your RISC-V. The runtime just can load this intermediate repetition to do machine inference. Actually, we call them together now graph compiler. So you see, it's still hard to run native AI application on this machine learning framework for RISC-V. So I will propose this solution before. So basically, we can expose remote machine learning framework from the remote to the local RISC-V. So simply put, wherever you deploy your RISC-V actually can access to some other architecture-based platform, either x86 or ARM64-based platform in many cases, right? This platform often can have that great AI ability offered. So we can leverage them to empower native AI for RISC-V. What I'm doing here now, basically, we deploy the machine learning framework on your RISC-V, even that trimmed down version of that machine learning framework with those necessary path module interfaces. And then we can use that transparent procedure call to let that module or that machine learning framework deployed on remote host to export those modules you need on your RISC-V. So with this way, we can support that native AI application on RISC-V. But obviously, it depends on remote AI ability. So I think it's not good. So I think now we can go a step forward. We can leverage the graph compiler locally and directly. Before I talk about the solution, just let's elaborate a bit graph compiler. So in terms of the machine learning software stack, we can divide that into 3 layers in this way. On the top layer, the machine learning frameworks, TensorFlow, PyTorch. They just serve engineering, offering them a high-level programming library with modern programming language like Python. On the bottom is low-level device driver and the library. They can just operate your hard device. Between them, the computation graph. The graph compiler is here. The purpose of graph compiler is to optimize the processing of forward or backward pass over the computation graph. The compiler just perform optimization at several levels, like graph rewritten and kernel fusion and the memory allocation. There are a lot of the existing graph compiler, like open source TVM and NVIDIA TensorRT and Intel OpenVINO and others. They are just targeted to the different AI accelerator. For RISC-V, we also have some graph compiler available. But most important thing is you should realize the graph compiler is more like third-party software. What does it mean? So you need to install and deploy graph compiler on your platform. And you need to write AI application with them. You also need to convert that model to that intermediate reputation manually. For this, also you need to know some model parameters to help complete this model compilation. So this thing just turn out, it's really, just as I said, it's not easy to run that native application on this machine learning framework for RISC-V. So I think it's not good to bring that RISC-V into the machine learning AI. So I'd like to introduce our transparent acceleration. So basically, we enable that empower machine learning framework by integrating this graph compiler, but seamlessly. So, but how? In order to achieve this goal, we design a system being automated and backend, because we don't want to introduce any additional efforts to a user, or due to that graph compiler, runtime, even our solution itself, or whatever. And it's also a server system, so it can be easily extended to support the machine learning framework and machine learning graph compiler. With this kind of implementation, this can be transparent to a user. How can we make this out? So definitely we'll build this graph compiler into your platform, but more importantly, we introduce our unique interposer. With the interposer to interact with the machine learning framework and talk to that graph compiler. But now the graph compiler just work as that backend. So it's a high-level layout, and you see here that we have that machine learning framework installed on your platform. A wide variety of graph compiler can be enabled to your platform. And then our interpose just can work closely with the machine learning framework and the graph compiler. It's like that bridge between the machine learning framework and the graph compiler. This high-level architecture, I think we can start from the computer node. We first deploy a system agent on your platform. Now, this agent can help us connect some hardware configuration, like your CPU type, your CPU number, and memory, and others. With this information, our manager can set up the server system with a backend and a graph compiler. By default, I like to use that open source TVM. But if your platform, your hardware can support that multiple graph compilers, you can reconfigure this by means of our controller as you need. So after that, we enable our interposer to machine learning framework. So what's going to happen next? So with our interposer, we are able to catch up in the machine learning framework API and just pass down to that graph compiler. Let the graph compiler to take a real operation, something like here, or to compile that model and even do that machine learning inference. We also can cache and save that pre-compiled intermediate repetition to speed up this. So I'd like to talk a bit more about our runtime interpose, because this is key of our solution. When you run your native AI application written on this machine learning framework for your RISC-V, so our runtime interpose can identify and intercept that necessary API from your machine learning framework and map them to that graph compiler API. Let me give you an example, like TensorFlow. Think of that one simple TensorFlow-based Python AI script. So typically, you should first call one API load model or load this to load your pre-trained model, and then call another API predict to do machine learning inference. So we just figure out some way to at runtime redirect load model to our customized load model, or predict to a customized predict. In our load model, we can get your model, right? And then we can pass the model automatically to get some model information, necessary model information, like model input name, model input shape, model output shape, and even model data type. Then we can let that graph compiler compile that model to that intermediate repetition automatically. In our predict runtime from the graph compiler, just load that intermediate repetition to do a real machine inference via your input. After that, we just get the result back to TensorFlow and back to your AI application. So now I think you can understand that now it's transparent to users, there's no code change to your native AI application. Next, I'd like to show two demos. So the first one is my RISC-V target. I first open one Python AI script. What does it do? Actually, just can recognize the image you input. It's more like the label image. You may find actually it's a TensorFlow-based Python AI script. It's native without any modification. Okay, let's run this. Fortunately, this platform can support the TensorFlow Lite, but I wanted to show we can empower the TensorFlow Lite by our backend graph compiler, this mechanism. So enable our server to enable that backend acceleration. Actually, we can support this through that REST API. Anyway, now just reopen this file to go through that very quickly to show, this is the same file, original file, there's nothing changed. Okay, now we can run that with the same command line. This time, you can see all those stages just as I talked about. Yeah, you can see we can at runtime intercept the TensorFlow Lite. We can get that model. We can pass the model automatically and get those information and auto compile the model to that intermediate repetition. We can at runtime to do real machine learning inference with your input instead of TensorFlow Lite itself. And you can see the result is the same, right? Actually, graph compiler always can reduce that inference time to boost your performance. Next, actually, I built our solution now into that Jupyter. You may know that Jupyter is one of the industry most used data science tools. I just built our solution as a Jupyter kernel extension. So when you launch the Jupyter server on your RISC-V, we can open that through this web browser like this. Now you can see that to that Jupyter kernel instance, right? The left is original, the right is enabled by our that extension. Like last demo, just run some similar source code in the original that Jupyter kernel instance. Okay, next I want to run same source code in this Jupyter kernel, but with our extension. Just copy the same source code to here to run it. You can imagine, no surprise, you can see that same output. Yeah, like this. So I want to say, our solution can be easily integrated to any that data science tool like Jupyter. Okay, here let's sum up. So in order to support native application written on the machine learning framework for your RISC-V, you even don't need the machine learning frameworks are fully supported on your RISC-V or supported very well, because we can empower the machine learning framework with that supported graph compiler. With this, we can support the native AI application for your RISC-V. And it also can guarantee that the best performance, because just as I said, the graph compiler offered by the vendor are always being developed towards that optimization for their own RISC-V. And even on the other side, in the future, for the RISC-V-based host, this will also can help support that diverse AI accelerator, because our solution can support any graph compiler to support different AI accelerator. So our solution just offer great ability to let you run a native application on RISC-V. I think the greatest advantage is such zero code change to your native application, but with the best performance. What's next? So basically, we make that graph compiler work as a transparent backend seamlessly to empower native AI for RISC-V. I'd like to see more graph compiler and more framework enabled. And to further explore if we can build this into those cloud-native machine learning frameworks. I also want to build this WebAssembly on RISC-V with this backend acceleration. I already built that on other architecture. I think if I can get this into that RISC-V as well, we just need one universal WebAssembly AI binary, which can be dispatched to everyone to really empower AI everyone for including that RISC-V. I think that's all. So I'm not sure if I have time. Okay. So anyway, if you have any question, just reach out to me through email, or maybe we can talk about somewhere after the talk. Thank you, everyone.